In this video, we're going to review electronegativity and how we can use electronegativity values to determine if a bond is ionic, polar covalent, or non-polar covalent. So remember that if you go to your periodic table, you can get a value for the electronegativity of every element. It's just a little number found at the bottom of the element square for a particular element. And what that value indicates is the tendency of that element to attract electrons to itself in a bond. So if you have a higher electronegativity, you're more likely to attract electrons closer to yourself in a bond compared to something that has a lower electronegativity. So to determine the type of bond that you're dealing with, you need to calculate what's called an electronegativity difference. Electronegativity difference. And we represent that by delta En, where delta means difference or change in the electronegativity value between two atoms. When you do that, there's three results you can get. You can get that your bond is ionic. You can get that your bond is polar covalent. And you can get that your bond is non-polar covalent. Ionic is essentially the idea that your difference in electronegativity is so high that an electron transfer has to occur. You can't share. One element has such a high electronegativity compared to the other, it just rips the electron away, essentially. And usually you're going to see that when your electronegativity value or difference is greater than or equal to 1.7. And these values will differ depending on what scale you're looking at. For our scale, we're going to focus on greater than or equal to 1.7. For polar covalent, the covalent indicates that there's a share, but the polar part indicates that the share is unequal. So the difference between the two elements is high enough that, or is low enough that they can share, but high enough that it's not an equal share. One of the atoms holds the electrons a little bit closer to itself compared to the other. And typically for this, we're going to see an electronegativity difference that's less than 1.7, but greater than 0.4. And then lastly, for a non-polar covalent, that's where you have a share that's indicated by covalent. And the non-polar part indicates that it's an equal share. So the electronegativity difference between the two atoms is so small that they share the electrons fairly equally. And so usually you'll see that when the electronegativity difference is less than or equal to 0.4. There is one more little category you might get, which is still part of the non-polar part. It's called pure covalent. So pure covalent. Pure covalent is where the electronegativity difference is equal to 0. And so that means that you're basically dealing with the same atom bonded to itself, like H2. Because if you do the difference in electronegativity between H and H, it's going to be 0. It's a pure equal share. Other non-polar covalents that aren't equal to 0, even though we say the share is equal, in reality, it's a little bit unequal. But for our purposes, we can classify it as being non-polar based on since it'll provide non-polar properties to the molecule. So we're going to go and do some examples of using electronegativity values to determine if a bond is covalent polar, covalent nonpolar, or ionic. As we mentioned, the values of electronegativity can be found in your periodic table, and our periodic table can be found just at the very top of our main calendar here. You can open up the periodic table, and you can find the values of electronegativity just at the bottom right of the element square or element box. So we're dealing with Si, and let's see, what was the element in this question? Si and P. So let's go to Si over here, 1.8. P is 2.1. So we're going to do the electronegativity difference is going to be equal to 2.1. So you always do the larger one minus the smaller one, which is 0.3. Since 0.3 is less than 0.4. This bond is a non-polar covalent bond. So that means the share is roughly equal. Not exactly 100% equal. It'll be a little bit more towards the phosphorus with the 2.1, since that's more electronegative, but it's still pretty close to being equal. So next we'll try the bond between C and F. So the electronegativity difference between C and F is going to be fluorine's the highest electronegativity value with 4.0, and C is 2.5. So 4.0 minus 2.5 gives us 1.5. So since this 1.5 is greater than 0.4, but less than 1.7, this is a polar covalent bond. Now, typically with bonds that are polar covalent, you can indicate where the electrons want to hang out more around using a bond dipole or a dipole vector. It's just an arrow that points in the direction of where the electrons want to spend more time. So for this, I would draw out CF. The more electronegative atom in this bond is F, indicated by the higher electronegativity value. I make an arrow that points in the direction of F, and I put a little vertical line there to show that the carbon side is slightly positive. The reason that F is going to be partially negative is because the electrons will spend more time around F compared to carbon, and carbon will be partially positive. This symbol I put here is a lowercase delta, which indicates a partial charge. It's not a full charge because we're still sharing, we haven't transferred. To be a full charge, you need to fully transfer the electron in an ionic bond. But when you have a polar covalent bond, you indicate partial charges only. So since the electrons spend more time around fluorine, the fluorine end of this bond, this is not a molecule, it's just a bond. It might be part of a larger molecule, we don't know. But the fluorine end will be partial negative, and the carbon end will be partial positive. And so this here is called a dipole vector. And it just indicates where the electrons, where the electron density distribution is based on the electronegativity values of the atoms you're dealing with. We'll do one more main example together, the bond between Na and Cl. And a lot of you can probably already tell what it is because you have a metal in there that is probably going to be an ionic bond. But let's just confirm, because you don't always have to have ionic between metal and non-metal, but you'll usually see it. So let's go to our periodic table to find the electronegativity values of Cl and Na. We have 3 for Cl, 0.9 for Na. So we have 3.0 minus 0.9 gives us 2.1. Since this 2.1 is greater than 1.7, we have an ionic bond. And it's with ionic bonds that we have full charges, because remember that we lose an electron when it comes to sodium, it becomes +1, and chlorine gained an electron, it became -1. And these are full charges, not partial charges, because they're not sharing. So that was looking at polarity of bonds specifically. Now what we'll do is we'll take a look at a molecule and we'll analyze all the bonds within that molecule, one at a time essentially. And the reason we do that is because eventually we're going to have to determine the polarity of the overall molecule. And to do that, you have to look at each of the bond polarities. So here's a molecule, CH2O. It's drawn out here. And what we're going to do is we're going to calculate the different bonds that exist here. So we have a CO bond. Whether it's double, single, or triple doesn't make a difference. This is a CO bond here. We want to find out if it's polar, nonpolar, or ionic. So I'll do my electronegativity difference between carbon and oxygen. And you'll see that it's 3.5 minus 2.5. And that gives us 1.0. And so what this means is that we have a polar covalent bond. And if you want to show that bond polarity, we could simply do an arrow pointing towards oxygen since it's more electronegative, and it would be a partial negative charge, and on the carbon, a partial positive charge. And so what we saw here is the polar covalent example. And that's when you have an electronegativity difference that's greater than 0.4, but less than 1.7. Let's take a look at the other bond in here. There's a CH bond. The electronegativity difference is for carbon 2.5 minus 2.1. For hydrogen, that's 0.4. And as we saw, if you have 0.4 or less, then that's considered non-polar covalent. And at that point, we wouldn't really have to draw in partial charges or dipoles because it's a roughly equal share. So if you have an electronegativity difference that's less than or equal to 0.4, we say that you have a non-polar covalent bond, an equal share. And then this bond, of course, is the same. It's a CN bond, 2.5 minus 2.1, a CH bond, sorry, and that gives you 0.4. Therefore, also non-polar covalent. So this here is polar. This bond here is non-polar. And this bond here is non-polar. So I could ask you to calculate bond polarity, which means look at the individual bonds and determine if they're polar or non-polar or ionic. And I could ask you for the overall molecule polarity. And that is looking at all of the individual bonds in a molecule and then making a judgment call as to whether the overall molecule is polar or not. We'll see that in more detail in the next video, but for now, let's just summarize the last type of bond, which was ionic, an electron transfer, and that's when your electronegativity value, delta, it's a triangle, En, is greater than or equal to 1.7. So in the next video, we're going to go ahead and take a look at the polarity of the entire molecule rather than just the bond polarity. And we'll learn some tips and tricks to classify molecules as either being polar or non-polar, because we'll need to know that so that we can predict properties of different molecules when they're presented to us.